Bioenergy from Indian sugar industry, a sustainable renewable energy future. Abstract: India is the world's second largest sugar producer during 2019 to 2020, narrowly losing the top spot to Brazil. India produced 28.9 million metric tons of sugar, which is about 17% of the world's total sugar production of 166.18 million metric tons. Also, the country expects sugar production to rise by around 17% for 2020 to 2021. However, the Indian sugar industry lacks in sustainability due to imbalances in demand-supply of sugar. The Indian sugar industry is faced with a reality that sugar, molasses, and bagasse can no longer be regarded as final product from sugar industry, and thus, value additions, diversifications and transformations to be vigorously investigated as possible routes to new market and making sugar industry less dependent on single commodity, i.e. sugar. The future of the sugar industry, as a whole, lies in development of sugarcane biorefineries, i.e. bioelectricity, bio-ethanol, biogas/bio-CNG, bio-manure, bioplastic and chemicals, etc. Keywords: biomass, bioethanol, bioelectricity, biogas, bio-CNG. Introduction. Conventional sugar factories process sugarcane to obtain crystal sugar, molasses, and energy CO products from bagasse. At present, only about 50% of the Indian sugar factories are carrying out power export to national grid, whereas, the number of ethanol units attached to sugar factories is bit higher. Hence, the potential of value addition through better utilization of byproducts even in the most common manner is not fully harnessed. Utilization of byproducts even in the most generalized manner, thus, can not only perk up the financial health of the sugar industry but also in meeting the scarcity of power and ethanol for EBP program, the bioenergy in either case. Moving further, a biorefinery includes the sustainable processing of sugarcane into range of valuable products, including food, feed, molasses, and chemicals, and energy, including power, fuels and heat, and thus, offers great potential for improving profitability and sustainability of the Indian sugar industry. 1. The sugar industry across the globe is also required to work on the mandate developing wealth from waste or converting waste to resource, utilizing anything which is available with sugarcane or is generated in one or other form of processing. Thus, for sustainability of the Indian sugar industry or sugar industry as a whole, it includes improvement in the sugarcane and sugar productivities, conversion from single product to multi-product factory, optimizing cost of sugarcane processing, integration with food processing industry, utilization of huge infrastructure during off-season, adoption of hybrid system for power generation, i.e. biomass, solar, wind power, and finally conversion of existing sugar factories to biorefineries. In terms of bioenergy, the major sugarcane energy chain/sources are bagasse for heat and bioelectricity generation, molasses for conversion to bioethanol, press mud and spent wash for conversion biogas, biocomposites pulp lignin ethanol/biocrude chemicals particle board tableware chemical bioplastics cattle feed baking/candy making biofuels pharmaceuticals industrial products fertilizers biogas/bio and wax proteins plant made products high value chemicals renewable electricity. Fig.1 Biorefinery concept. Bioelectricity. Sugarcane is one of the most promising agricultural sources of biomass energy in India and elsewhere. In sugarcane plant the overall percent by weight of dry matter and the energy content is given in Table 1. At present, only sugarcane stalk is processed to extract juice and bagasse, the fibrous residue left over after the milling. The balance 37.37% of energy of the sugarcane plant remains unutilized. This energy needs to be used efficiently. It is fact that for the soil conditioning and its fertility improvement, part of the sugarcane plant residue, SPR, should be used in mulching. Even if 50% of the SPR is left for mulching, the balance 50% of SPR is a huge source of bioenergy, and efficient utilization of the same may enhance the revenue of the sugar industry to a greater extent. The revenue generation for a 5000 TCD plant in respect to utilization of 50% SPR is given in Table 2. Bagasse is usually combusted in boiler furnaces to produce steam for power generation, but now is also being considered as an emerging and attractive feedstock for 2G bioethanol production. It is also utilized as the raw material for production of paper, particle board, and tableware, etc. Bagasse-based CO generation is one of the most attractive and successful power projects that have already been implemented in many of sugar factories in India. Combined heat and power from sugarcane in the form of power generation offers renewable energy options that promote sustainable development, take advantage of domestic resources, increase profitability and competitiveness in the industry, cost-effectively address climate mitigation and other environmental goals. For efficient utilization of biomass, bagasse-based CO generation in sugar mills have been promoted by CO generation program under Ministry of New and Renewable Energy, MNRE, Government of India. Most of the sugar factories in India, cogeneration units work at very low cycle efficiency. For 67 ATA and 87 ATA pressure, the cycle efficiency is as low as 15 to 18% only, whereas it is between 21 to 25% for 110 ATA and 125 ATA pressure. Power plants operate at cycle efficiencies as high as 35 to 45%. To improve upon, the working pressure and temperature needs to increase up to 140 ATA and 560 degC so as it may reach up to 35% of the efficiency. Another factor which needs to be improved for increasing the pressure and temperature is the moisture content of bagasse. Moisture of bagasse is to be brought down to as low as possible by use of waste heat going out of chimney. Details of cycle efficiency and power generated is given in the Table 3. Advantages of bioelectricity. Generating bioelectricity offers numerous benefits as 1. A rich and renewable source and of high potential to substitute fossil fuels to meet energy demands of the country. It is also less expensive than fossil fuels. 2. It provides clean and green energy because of neutral emission of carbon dioxide, CO2. 2. 3. Decentralized power generation results minimal transmission and distribution costs. 3. 4. It enables diversification in electricity generation, thus, increasing energy security. 5. Significant reduction of environmental pollution in relation to use of fossil fuels. 3. 6. It helps sugar mills to meet 100% of their energy needs and drastically reduce their operational costs. Furthermore, the opportunity to sell surplus electricity to electric power grid. 4. 7. Additional revenue generation through sale of carbon credits in terms of Clean Development Mechanism, CDM. 5. And Renewable Energy Certificate, REC. 8. Improved gross station heat rate, SHORE, of 5,500 kcal/kWh with high-pressure boiler/turbine combination. 9. Assists in modernizing the rural areas by promoting sustainable rural growth. Indian electricity sector scenario. The utility electricity sector in India had an installed capacity of about 382.0 GW as on March 2021. Renewable power plants constitute 94.4 GW, i.e. about 25% of total installed capacity, out of which, contribution of biomass-based. Cogeneration power is 10.0 GW, i.e. 11.0% of total installed renewable energy sources, RES, capacity. Residential includes small hydro projects, biomass power, urban and industrial waste power, solar and wind energy. Fig.2. 61.4%, 1.8%, 12.1%, 10.3%, 10.5%, 1.3%, 2.7%, 0.0, 10.0, 20.0, 30.0, 40.0, 50.0, 60.0 thermal, nuclear, hydro, wind, solar, small hydro, biomass percent contribution. Fig. 2. Installed power capacity in India as on March 2021. Source: CEA data March 2021. During last 5 years,
the installed biomass power capacity has increased by about 130% and achieved targeted capacity of 10.0 GW in early 2020, in which the bagasse-based CO-generated power played a vital role. Fig.3. The current exportable energy from excess bagasse in sugar factories is about 3,500 MW, which is 1.0% of the national electricity generation, with only part of the sugar factories undertaking power export and also as only about one-third sugar factories out of 275 CO-generating sugar factories have high-pressure CO generation system. With the availability of advanced CO generation technologies, sugar factories can harness the on-site bagasse resource to go beyond meeting their own energy requirements and produce more. Keeping in view the average cane crush of 300 MMT during a crushing season, the potential of the sugarcane industry nationwide is estimated as around 12.5 GW that can be exported to the grid on the basis of power generation at around 150 kWh per tons of cane processed using the latest commercially proven CO generation technologies. New technologies like steam parameters with extra high pressure and temperature configuration, modified design of fuel handling system and furnaces, higher blending of other biomass along with bagasse, improvements in pollution control devices and water treatment plants etc. have to be made to increase the potential to this level. The exportable power potential may be further increased by around 15%, i.e. to 14.0 GW after installation of bagasse drying system 6. Table for power export potential in different models of CO generation. MMT million metric tons. Presently direct combustion technology to generate steam for production of electricity through condensing extraction steam turbine, CEST, system is dominant, but the future is focused on the introduction of high-efficiency gasification combined cycle system 7. In this system gas turbines fueled by gas produced by thermochemical conversion of biomass. The exhaust is used to raise steam in heat recovery systems used in expanding through a steam turbine to boost power output and efficiency in a gas turbine/steam turbine combined cycle, GTCC. Gas turbines, unlike steam turbines, are characterized by lower unit capital costs at modest scale, and the most efficient cycles are considerably more efficient than comparably sized steam turbines. Fig.4. Biomass dryer gasifier gas cleaning gas turbine steam turbine heat recovery steam generator GG flue gases. Fig.4 simplified schematic of a biomass integrated gasifier/gas turbine combined cycle, BIG/GTCC, system. The potential of power generation in such case may as high as 225 to 250 kWh per ton of cane as compared to 120 to 150 kWh through CES system. Bioethanol. Increase on world's energy demand and the progressive depletion of oil reserves motivate the search for alternative energy resources, especially for those derived from renewable materials such as biomass. Global concern about climate change and the consequent need to diminish greenhouse gases emissions have encouraged the use of bioethanol as a gasoline replacement or additive. Bioethanol may also be used as raw material for the production of different chemicals, thus driving a full renewable chemical industry. In recent years, energy consumption and global carbon intensity, the ratio between carbon emissions and energy supplied, have increased worldwide, reinvigorating worries about potential depletion of fossil fuel reserves. Such increase, accompanied by growing political instability in oil-producing regions, has instigated many countries to search for alternative forms of energy aid. In most cases, this alternative source is renewable, since the CO2 emitted into the atmosphere is recaptured by the growing crop in the next growth cycle. Ethanol from sugarcane is one of the most promising biofuels because its energetic balance is generally positive, meaning that the growing sugarcane absorbs more carbon than is emitted when the ethanol is burned as fuel. Ethanol, ETOH, may be produced using sugarcane bagasse as raw material through the organosolve process with dilute acid hydrolysis, thus increasing ethanol production with the same cultivated sugarcane area 9. The area, however, requires an intensive study before adopting it on commercial scale with respect to economics of production and comparative advantages between power generation vis-a-vis ETOH production. U.S. Environmental Protection Agency, EPA, classified that sugarcane ethanol as capable of reducing greenhouse gas, GHG, emissions by at least 50% compared to gasoline 10. Roughly, 1 ton of sugarcane biomass based on sugar, bagasse, and ethanol output has an energy content equivalent to 1.5 barrel of crude oil 10. The sugarcane plant, therefore, takes on special significance as the world's most economically significant energy crop and presents exciting opportunities as well as challenges if it is to reach its potential as a bioenergy resource. Overview of Indian alcohol industry. India is a fast-growing economy and is facing the challenge of increasing energy demand, which is usually met by fossil fuels. India's domestic production of crude oil since been inadequate to cope up the requirement. This huge gap between demand and supply is met by imports at the cost of foreign exchange draining out. Ethanol is such a fuel which can partially or fully replace fossil fuels. In India, at present, for the proposed 10% blending, approximately 3,500 million liters of ethanol is required. Ethanol in India is mainly produced by the fermentation/distillation of final molasses, i.e. C molasses, the byproduct and B-heavy molasses of cane sugar industry. The production of C molasses in India, under normal circumstances, is about 12 to 13 million tons per year, which can produce alcohol to an extent of around 2,800 to 3,000 million liters, out of which the produce is also utilized by potable and industrial sector. As a result of it, the blending targets of about 5% could be achieved with the amount of available ethanol obtained through the conventional IEC molasses route. India, at present, targeting ethanol blending at 10% in petrol, produces it mainly by molasses route. The installed capacity of about 6,500 million liters per annum, 3/4 molasses and 1/4 grain-based, is grossly underutilized due to shortage of raw material, i.e. molasses. Statistically, India produces about 3% and 1% of the world alcohol and fuel alcohol respectively. However, many policy interventions viz. Financial assistance for setting up new ethanol plants/expansion of existing plants and differential pricing policy for ethanol made out of various feedstocks from sugar factories, i.e. C molasses, B-heavy molasses, cane juice/syrup/sugar have been made to ensure higher availability of ethanol in future. Table 5 Molasses and estimated alcohol production potential. Considering 5% diversion of molasses for export, cattle feed, other uses, and wastage/deterioration etc., and assuming an average realistic yield of alcohol at 235 liters/ton of molasses, considering average total reducing sugar content as approximate 47.5. Sugar. All figures in million liters. It is pertinent to mention that during 2020 to 21, the potential of alcohol production from sugar industry is about 2,800 million liters through C molasses route and about 1,200 million liters through sugar cane juice and B-heavy molasses diversion route. The requirements for potable liquor industry and other industrial uses is about 1,500 and 500 million liters respectively. Even if the 500 million liters of alcohol production is considered from grain-based distilleries, 2,500 million liters of ethanol shall be available for National Ethanol Blending Program, EBP, which shall be sufficient for about 6.5% of the blending target. Keeping this in view, to achieve the blending target of 10%, there is need to encourage more utilization of alternative feedstocks available with the sugar industry viz. B-heavy molasses, sugar cane juice, and sugar syrup may be considered to cope up with the requirement. Under the situation of excess sugar production, lower sugar prices and favorable market economics, diversion of sugar cane juice or diversion of other intermediate molasses, B-heavy molasses, holds promise considering the relative economics of ethanol vis-a-vis sugar production. The ethanol production from cane juice and B-heavy molasses is reported to be about 70 to 75 liters/ton and 300 to 330 liters/ton respectively. the diversion shall result into 1. Better capacity utilization of the distilleries. 2. Variation on the ratio of sugar and ethanol produced according to the market, resulting in sugar price stabilization and coping up with the requirement of ETOH for EBP. 3. Sugar of better quality, no need to recycle molasses or juices of low purity and thus price premium over the produce. In addition to this, the conventional distilleries may be converted to smart distilleries utilizing other alternate feedstocks available in different regions of the country. The potential of ETOH production may be harnessed by utilizing cassava, sugar beet, and sweet sorghum as available in different agroclimatic zones. As discussed earlier, more work shall be required to develop a cost-effective, indigenous technology for production of ETOH from lignocellulosic material including bagasse. Apart from the above, considering the ample amount of available grains which is not found suitable for human consumption may be utilized for production of ethanol by converting the existing molasses-based distilleries into dual feedstock-based distilleries. The Government of India has already announced policy in this regard, and it is expected that more dual feedstock-based ethanol units shall be set up in future. A holistic approach on the above will result into integration of more distilleries with the sugar factories, optimal capacity utilization of the existing distilleries and increased availability of alcohol for all sectors, resulting into a win-win situation for all the stakeholders. Biogas and bio-CNG. Conventionally, handling of the filter cake in the sugar industry is considered to be a troublesome area, and whatever utilization is made is in making the biocompost. However, in pursuit of generating higher revenues, the unharnessed potential of filter cake has been exploited by utilizing for generating biogas or bio-CNG/CBG. Filter cake contains appreciable proportion of biodegradable organic matter which has very good potential for the production of biogas from it. Biogas from filter cake can be produced by anaerobic digestion, which is a biochemical degradation process wherein organic matter is decomposed by bacteria in the absence of oxygen. 11. The anaerobic digestion is low-cost method, and the byproducts of this process are methane, CO2 and H2S. It is a complex process and divided into 4 categories: hydrolysis, acidogenesis, acetogenesis or dehydrogenation, and methanation. Fig.5, the use of biogas or compressed biogas/bio-CNG will not only help to preserve the non-renewable energy resources but will also decrease dependence on scarce fossil resources and will also lead to decrease in greenhouse emission and earning additional revenue in case of sugar factories. In addition to that, in our day-to-day life we come across different types of waste such as municipal solid waste, food waste, industrial waste, sewage sludge, animal manure, and agricultural residue etc. Having the good energy potential may be converted into biogas/bio-CNG. Carbohydrates, proteins, fats, sugars, fatty acids, amino acids, carbonic acids and alcohols, hydrogen, carbon dioxide, ammonia, hydrogen, acetic acid, carbon dioxide, methane, carbon dioxide, hydrolysis, acidogenesis, acetogenesis, methanogenesis. Fig.5 Anaerobic digestion process. It has been estimated that 1 ton of press mud generates between 85 to 120 cubic meters of biogas, i.e. 25 to 30 kgs of filter cake yields about 1 kilogram of bio-CNG, and thus looking to the prices of filter cake and bio-CNG being about $2.50 per mount and about $48 per kg respectively. Utilization of filter cake in such a manner appears lucrative for value addition and for providing green energy. Potential of compressed biogas, CBG, from Indian sugar industry. The graphical presentation at Fig.6 provides an idea of total compressed biogas potential in the country, estimated to be about 62 million metric tons per annum, out of which spent wash/filter cake, press mud, can contribute to the extent of about 2 million metric tons. 20 MMT 32%, 25 MMT 40%, 2 MMT 3%, 5 MMT 8%, 10 MMT 16%, 051015202530354045 surplus agri residue or recoverable cattle dung, chicken litter, spent wash/press mud, municipal solid waste, sewage treatment plant percent contribution. Fig. 6 Compressed biogas potential.
Bioenergy from spent wash, biomass. It may not be out of place to mention that biomass/spent wash, the effluent of ethanol production, may turn out to be a key source of bioenergy, either by transforming it into biogas, methane, which can be used as boiler fuel, or after concentrating it in multiple effect evaporators, and then to incinerate along with bagasse/coal/other biomass in an incineration boiler integrated with turbine to produce the bioelectricity. 12. Potential of bioenergy from spent wash. Keeping in view the average alcohol production of 3,000 million liters during an alcohol year, the potential of the alcohol industry nationwide is estimated around 500 MW power, as reflected in Table 7, that can be utilized for own process uses, and surplus energy may be exported to the national grid, using the latest commercially proven incineration technologies. Discussion. The optimal utilization of resources, with exploring new horizons besides facilitating bioenergy in the form of biomass power, bioethanol and biogas/bio-CNG, shall also help in maintaining the health of the sugar industry even under adverse sugarcane price scenario, thus making possible in-time payments for the sugarcane prices to the 50 million sugarcane farmers and others directly or indirectly associated with the Indian sugar industry, which has frequently remained a volatile issue. For the Indian sugar industry, the judicious utilization of the three vital byproducts, i.e. bagasse for bioelectricity, molasses for bioethanol and press mud for biogas/bio-CNG, can bring a turn around the situation, as reflected from Table 8 and Table 9 respectively, as besides rendering green energy, it renders the most desired value addition by the most convenient route. The potential of bioethanol shall be further increased by diversion of sugarcane juice or B-heavy molasses, considering the relative economics of ethanol. Conclusion. Production of bioenergy is one of the most proficient ways to achieve sustainable development. Increasing its share in the worldwide matrix will not only help prolong the existence of fossil fuel reserves, address the threats posed by climate change, but also enable better security of the energy supply on a global scale. Most of the new renewable energy sources are still undergoing large-scale commercial development, but some technologies are already well established. These include bioelectricity and bioethanol, in particular, which is a global energy commodity that is fully competitive with motor gasoline and appropriate for replication in many countries. In the near future, the bioenergy concept of complete utilization of sugarcane biomass, molasses, and press mud will become a pivotal element for a sustainable sugarcane industry. An industry that produces bioelectricity, biofuels, and biogas/bio-CNG fuels from a renewable source should be considered a fascinating vision. From the perspective of sustainable energy development, renewables are widely available, ensuring greater security of the energy supply and reducing dependence on oil imports from politically unstable regions. Renewable are less polluting, both in terms of local emissions, such as particulates, sulfur and lead, and greenhouse gases, carbon dioxide and methane, that cause global warming. Hence, there is abundant opportunity for the wider use of bagasse/spent wash for generation of bioelectricity, molasses for production of bioethanol and press mud for production of biogas/bio-CNG in sugarcane producing countries. Even, this potential remains by and large unexploited.